We have seen ideal filters in previous modules, and we have also seen that these filters cannot be implemented in practice. So in this module, which is the first in a three-part series on filter design, we will start looking at strategies with which we can approximate the behavior of ideal filters with practical structures. Our first strategy will be that of imitation. We will try to replicate the features of either the impulse response or the frequency response of ideal filters. But we will soon see that this strategy is rather limited, and we will have to get more creative in later modules. Welcome to Module 5.6 of Digital Signal Processing. This is the first part of a three-part series on filter design, and today we will talk about the approximation of ideal filters. We will see three fundamental methods to approximate the impulse response of an ideal filter: impulse truncation, the window method, and frequency sampling. So you remember, an ideal filter is not realizable in practice because the impulse response is a two-sided infinite support sequence. So we're going to try to approximate it by starting from the ideal impulse response and by manipulating this response into something that we can actually deal with. In the next examples, we will concentrate on the design of a low-pass filter, but clearly the same techniques can be applied to any type of ideal filter. So the first idea is the following. We pick a cutoff frequency omega c, we compute the ideal impulse response for the low pass analytically, and we truncate h of n to a finite support hat h of n. This hat h of n defines an FIR filter that we can use. For the time being, we don't worry about causality, so we preserve the symmetry around zero of the impulse response, and we approximate the ideal filter with an FIR of length 2 capital N plus 1 centered around 0. And so here, hat h of n is equal to omega c over pi times the sinc of omega c over pi n for n less or equal to capital N in magnitude, and 0 everywhere else. A justification of this method is the fact that if we compute the mean square error between the original filter and the approximation, we have that the norm of the error in the frequency domain is the integral from minus pi to pi of the frequency response of the ideal filter minus the frequency response of the approximated filter squared. This is equal to the norm squared of the difference between the two frequency responses, and thanks to Parseval's theorem, this is also the norm squared of the difference between the impulse responses in the time domain. And so we can write that the mean square error is simply the sum from n that goes to minus infinity to plus infinity of the difference between the two impulse responses squared. The impulse response of the ideal low pass is the sinc, and you remember it decays monotonically as 1 over n. So the mean square error is clearly minimized if we pick values for hat h of n from an interval that is symmetric around 0, because in this way we're actually killing in that summation the largest terms. So we have seen why impulse truncation might be a good idea, but it's time to look at why it might not be such a good idea after all. And to appreciate that, we have to look at the frequency response of the approximate filter. So here in this plot, we show the frequency response of an ideal low-pass filter, where we choose omega c equal to pi over 2. And superimposed, we're going to show the frequency response of the approximate filter for increasing values of capital M. So we start with m equal to 9, which is not really a very long filter, and we see that the approximation is not particularly good. So we increase the number of taps of the filter, and as we add more and more points to the impulse response, we see that the characteristic in red approaches the characteristic in green. But it looks as though the maximum error near the transition point for the frequency response never really goes down in spite of the number of points that we use for the approximation. We can try and push the number of points even higher, and we see that even for 300 points, the maximum error around omega c is always of the same amplitude. We can prove mathematically that the maximum error around the cutoff frequency is about 9% of the height of the jump, regardless of the number of points. This is a standard result in approximation theory known under the name of Gibbs phenomenon. It always happens when we try to approximate a discontinuous function. In order to understand intuitively what happens when we approximate a filter by truncation, we have to take a little bit of detour and look at the problem from a different perspective. So we could consider the approximated filter hat h of n as the product of the original impulse response times a sequence w of n, which is just the indicator function for the interval minus n to plus n. So w of n is just a series of points of value 1 centered in 0 and going from minus n to n. So with this notation, the question now is, how can we express the Fourier transform of the filter as the product of two sequences? And for that we have to study the modulation theorem. The modulation theorem is really the dual of the convolution theorem. You remember the convolution theorem states that the Fourier transform of the convolution of two sequences is the product in the frequency domain of their Fourier transforms. The modulation theorem gives us a result for the Fourier transform of the product of two sequences and tells us that their Fourier transform is the convolution of the Fourier transforms in the frequency domain. So what is a convolution in the frequency domain? Well, in C infinity, i.e. in the space of infinite support sequences, we can define the convolution in terms of the inner product between two sequences. So the convolution between x and y is the inner product between x conjugated with y time reversed and delayed by n. And so if you apply the definition of the inner product in C infinity, that's exactly what you get. We can adopt the same strategy in L2 of minus pi pi, which is the space where DTFTs live, and define the convolution between two Fourier transforms as the inner product between the first Fourier transform conjugated and the second Fourier transform frequency reversed and delayed by omega. And if we apply the definition of the inner product for L2 of minus pi pi, we get that the convolution between two Fourier transforms is 1 over 2 pi times the integral from minus pi to pi of big X of e to the j sigma times big Y of e to the j omega minus sigma in this sigma. With this notation in place, we can prove that the DTFT of the product of two sequences is the convolution of their Fourier transforms by working backwards. So we start with the inverse DTFT of the convolution of two Fourier transforms. We can write it out explicitly like so. And if we expand the definition of the convolution inside the integral that defines the inverse DTFT, we have the following expression, where here you have the convolution and outside here you have the inverse DTFT. Now we use the same trick that we used when we proved the convolution theorem, namely we replace omega with omega minus sigma plus sigma in the exponential here. And we managed to split the complex exponential in a way that will allow us to separate the contribution due to x and to y. And indeed, when we do so, we have a first part here, which is just the inverse DTFT of big X, and here we have the inverse DTFT of big Y. The fact that the argument to the complex exponential has a minus sigma term doesn't really bother us because the integral is between minus pi and pi, and of course the DTFT is 2 pi periodic, so an offset does not change the result of the integral. And so finally we have indeed what we were looking for, the product of the two time domain sequences. As an interesting aside, let's look back at the sinusoidal modulation result with the help of the modulation theorem we just studied. So the DTFT of a sequence x of n multiplied by cosine of omega c n turns out to be the convolution of the DTFT of x with the DTFT of the cosine of omega c n, which is 1/2 delta of omega minus omega c plus delta of omega plus omega c. This delta here is the delta defined over the real line, so it's that functional that isolates the value of a function when it is used under the integral sign. So because of the distributive property of the convolution, we can split the above convolution product into two terms, which we write out explicitly here as convolution integrals. And we have, for instance, in the first case, the integral of the product between the DTFT of x and delta of sigma minus omega plus omega c in this sigma. Similarly here, we have the complementary term on the negative axis, the integral of the product between the Fourier transform of x and delta of sigma minus omega c. because of the shifting property of the delta, these integrals will isolate the value for the Fourier transform for the value of sigma where the argument to the delta is equal to 0. So in the first case, we will have that the delta will kick in for sigma equal to omega minus omega c, and in the second term, it will kick in for sigma equal to omega plus omega c. And so in the end, the final result is the well-known modulated signal, 1/2 the Fourier transform of the signal centered in omega c, plus 1/2 the Fourier transform of the signal centered in minus omega c. So this is another way to arrive at the sinusoidal modulation result. But now we should go back to the reason why we started this detour into the modulation theorem and try to understand what the Gibbs phenomenon is all about. So remember, in the beginning of our detour, we were at a point where we had expressed the approximate filter hat h of n as the product between the ideal impulse response h of n times an indicator function that serves the purpose of isolating the points of the ideal impulse response that we want to keep. So if this is the ideal impulse response, h of n, and this is w of n, you can see that this window basically kills all these guys here and kills all these guys here and leaves us with an FIR approximation to the impulse response. In the frequency domain, this corresponds to the convolution of the Fourier transforms of the two actors. The Fourier transform of the ideal impulse response is the rect function that we know very well. The Fourier transform of the indicator function we have seen many times before. We have computed it for the first time in module 4.7, and it is actually the Fourier transform of a zero-centered moving average filter. So its formula is here, and it's sine of omega 2n plus 1 over 2 divided by sine of omega over 2. So here we're going to try and compute the convolution between the Fourier transforms in a graphical way. Here are the actors involved in the play. We have h of e to the j omega, which is the Fourier transform of the ideal filter. We have w of e to the j omega, which is the Fourier transform of the indicator function. And here we have the result, which is the integral of the product of these two guys. As omega moves along the axis here, we will recenter the Fourier transform of the indicator function, take the product of the two, and compute the integral. In the beginning, we're just integrating the wiggles of the function over the non-zero part of the ideal impulse response. So what we have is an oscillatory behavior of small amplitude. Things start to become interesting when the main part of the Fourier transform of the indicator function starts to overlap with the support of the rect for the ideal filter. As we approach the transition band of the filter, we see that the value of the convolution starts to grow. And as a matter of fact, it grows even more when the entire main lobe of the Fourier transform of the window is under the rect function. As we move along, the ripples that trail the main lobe start to get integrated, and so the behavior in the passband is again oscillatory as these little ripples enter and exit the main integration interval. As we reach the other transition band, we have exactly the symmetric behavior at the other edge of the band. The shape of the Fourier transform of the approximate filter will depend then on the shape of the Fourier transform of the indicator function. So if we look at it here, we see that we have what is called a main lobe, here in blue, that will determine how steeply the approximate filter will transition from the stop band to the pass band. The width of the main lobe is what determines the steepness, whereas the amplitude of the so-called side lobes will determine the amplitude of the error on either side of the transition band. And this is what determines the Gibbs phenomenon. So in terms of our requirements, what we would like to have is a very narrow main lobe so that the transition is very sharp. And at the same time, we would like to have very small side lobes so that the Gibbs error is kept low. And we would also like to have a short window so that the FIR will be efficient. And these are very, very conflicting requirements. There is a large body of literature that is concerned with developing the best possible window in order to approximate an LDO filter. For instance, we have used a rectangular window to truncate the impulse response, but if we use a triangular window, that therefore weights the impulse response and tapers it to zero in a more gradual manner, what we have is that we will be able to attenuate the Gibbs error at the price of a wider main lobe. So here you have the comparison between a 19-tap rectangular window in gray and a 19-tap triangular window in red, and you see that the side lobes are much smaller for the triangular window, but the width of the main lobe has increased. Let's move on now to a new method to approximate an ideal filter, called frequency sampling. The idea here is to say, what if we draw the desired frequency response in the frequency domain? Then what we do is we sample this frequency response at regularly spaced intervals, and then we compute the IDFT of this value, so the inverse DFT, which we can always do for a finite set of frequency points, and use the result as an M-tap impulse response hat h of n. Look at an example. We start with our classic ideal low pass with omega c equal to pi over 2, and say we pick m equal to 11, and we take 11 samples of this frequency characteristic between minus pi and pi. We rearrange them according to the DFT notation, and we compute the inverse DFT with a numeric algorithm. So if we do that, we get the following impulse response. This is an 11-point impulse response obtained by computing the inverse DFT of the samples of the ideal frequency characteristic. So if we take the Fourier transform now, so the DTFT of the finite support filter, well, what do we get? We need to convert the DFT representation to the DTFT representation. We know how to do that. We studied that in detail in module 4.7, and we know that the frequency response will be the interpolation in frequency of the frequency samples that we took in the first step. The interpolator turns out to be, once again, the transform of an n-tap rectangular window. So we're not really escaping from the indicator function that we used in the impulse truncation method. And because of that, we will have no control over main lobe and side lobes of the interpolator. Graphically, it looks like this. Here is the original DTFT in green. In gray, we have the frequency samples, and the resulting DTFT will be the interpolation of these frequency samples using this interpolator here in blue. When we do the interpolation, as we have seen in module 4.7, that is what we obtain in the end, and again we have a filter that will exhibit an error around the passband that we are not going to be able to control. In short, these methods to approximate ideal filters are certainly very useful when we want to derive a quick and dirty prototype and we don't have time to use more sophisticated filter design methods that we will see later on. So these are good methods to know in order to quickly try something out when we're faced with a filtering problem. But definitely they are not optimal, and they leave a lot to be desired in terms of the fine control that we can have over the maximum error.